Okay, we can start. First of all, I finished the slides last night. I didn't have the time to rehearse, and so bear with me. Maybe there are some errors, so feel free to interrupt whenever you want. Um, in this talk, actually, I want to discuss successor states and how to do reward-free RL in deep RL. And this is something I've been working on last year when I was in Ericsson. It's actually a really nice topic, in my opinion. I like it, and it has several connections, not only to reward-free RL, but also to multi-objective RL, and I think it can be applied in many settings. And the paper that got my interest initially, it's this paper, and it's actually a foundational paper, in my opinion. It's like 100 pages of stuff, but you don't really need to read 100 pages. It's easily accessible. The main theorems are just in the initial sections, and then most of the rest of the paper is just like extensions. So you don't need to read all the 100 pages, which makes it very nice. And if you read also the rest, it feels like an added bonus that, yes.
So your inner Alessio is not displeased.
No, it's not displeased. Although maybe you can maybe remove 20%. And just to give you an idea of what this work can lead to, I want to show you this website first. So here, I'm gonna give any reward function I want. It's a Mujoko environment. I'm gonna give any reward I want. For example, here I can write that I penalize high velocities, and it's gonna compute immediately the optimal policy for this reward and run the environment. So now it's running.
So can you inject some malicious code?
I didn't try. But yeah, it will start doing stuff. Now, I don't remember if this reward function is actually velocity times position, but here you also have some examples, like be upside down.
So it looks very similar to successor features.
Yeah. So be upside down. Makes sense, right? What's nice is that you can put any reward. So you don't have a finite set. It could be really anything. And I believe this is really cool. So that's why this paper really got my interest initially, that it's not only like theory, but it can also be applied in practice. So the theory is about learning successor states. Successor state model the expected future state occupancy, and they are also related to goal-dependent value functions that maybe you have heard sometimes. So I will talk about this. How can we train a deep RL thing that can do the same stuff? But we will go first through the theory. And all the references are these three papers, essentially. So we're going to talk about successor states in tabular domains, successor states in continuous domain, and how do we learn sparse rewards in continuous domains. And then the forward-backward model, which is a factorization of this successor measure. And this forward-backward model is also one particular way to extend the technique to deep RL. So that's what we are gonna talk about today. It's gonna be a bit long, maybe. Yes, successor states capture the expected future occupancy of a state, starting from some given state under a fixed policy. So you can think of it like a measure. And they have been studied widely in reinforcement learning, in goal-reaching problems. And learning successor states can be more efficient than learning separate value functions for each goal in general. So we start with some simple mark or reward process. There are no actions involved, but if you want actions to be involved, just think that there is a fixed policy. So we have a transition with a fixed policy pipe, and the successor state operator simply maps any starting state S to a measure over future states, which is defined in this way. So it's a sum of like discounted future occupancies. This is not really a probability measure because it's not normalized, but you can normalize it. And in the definite setting, M is simply a matrix, the usual matrix, I minus gamma P inverse. So this matrix, one element of this matrix, S prime, is the discounted expected number of visits to state S prime starting from S. So if we learn this object, then you can generalize to multiple rewards. So the idea is, how do we learn this measure? How do we learn M for tabular and continuous domains? And you can see that for any reward or any feature map of the states, we can see this connection between M and the expected total sum of this feature. So you can think of psi as the value and this phi as the reward. And then psi is gonna just be this integral over M of phi for the continuous domain, while in the tabular case, we have here this sum over states. So how do we learn M? How do we learn this measure? And this is not trivial for continuous domain. Maybe it's trivial for tabular domains.
Oh, yeah.
Yeah.
If there are no actions, it's just learning a Markov chain.
You can think that there is a fixed deterministic policies. So this policy always takes the same action for now.
You woke up.
Okay, so we for continuous domain, we need to work with densities. And in this case, we assume to know some dominating measure rho that we can use to define the density M through the Radon-Nikodym derivative. And usually this rho will be the data distribution induced by the policy that we assume it will cover the entire set space. In practice, it's going to be the replay buff at the end. So having done this, we can look at the tabular case. Well, I want first you to notice that this thing here, it's essentially a Bellman equation. You can learn it through TD learning. So that's what we are going to do in the tabular case. We can express M as the fixed point operator, fixed point of the Bellman operator. And the proof, I mean, it's simply based on the fact that it's this Newman series and there is a unique solution. So we can use TD learning to learn M. The tabular case, it's easy. It's also a contraction because we have the discount factor. Also here, the proof is rather simple. You could use value iteration then to learn M in the tabular domain if you know the transition matrix P. But if you don't know the transition function and you want to do stochastic approximation, so TD learning to learn M, that's what you can do. So we maintain a matrix M of size S times S, and upon observing a transition S to S prime, for all states, we do this update. So for all states S2, we update the matrix in S2 in this way, where this delta is like the TD error, and the TD error in SS2 is computed in this way. So it's like performing TD learning in parallel for each possible goal state S2. So you can think of states as goals and for each state, you update the matrix in this way. So learning M in the end is about really learning sparse rewards, learning this indicator function. And this is why it's going to be tricky in the continuous case. In the tabular case, it's doable, but in the continuous domain, can we really learn binary rewards like indicator functions? So yes, doing this in the tabular domain, it's really equivalent to doing TD learning on a state goal MDP, where essentially you augment the state with a goal value. And then the Q function for this state goal, it's going to be exactly what we learned with this TD learning. Okay, so far I think it was easy, right? Now we look at the continuous case, which is my favorite part. So obviously we cannot store a matrix when we have a continuous domain. Instead, the idea is to represent M through the density. So we parameterize a density, a function that represents the density, in this case M theta. And we also have this dominating measure rho. But we should also mention that in continuous spaces, M has a singular part because of the identity. And if you use a smooth parameterization, actually, it's not really able to capture this identity very well. So usually the measure M comprises a Dirac mass at S. But in practice, it's not really a problem. But anyway, so we parameterize M theta and little M theta, the density, and we also call capital M theta to be the corresponding measure of little M theta. And we know that ideally it is capital M theta satisfies the Bellman equation from what we have seen in the tabular case. So it's a fixed point of the Bellman operator. To learn this quantity, first, we need to define some notion of distance. So we define this norm, this rho norm. Here, this should be a squared, where f is defined in this way. So this is like, I define f to be in this way. It's not, it's because it's the density. Because of that Dirac mass thing I told you before, it's not exactly the same. So what we really want to do is to minimize this Bellman error. So we define this cost function, and we want to minimize this and hope that at the minimum we have a fixed point. So really exactly what we do in DQN, for example. But always from DQN, we also know that in deep parallel, this will not work. We need some stationary target. So we fix a theta bar, and we define the target M in this way to be the identity plus gamma P M theta bar for some fixed theta bar. So we fix the target and we do one gradient step on theta. But the problem is in continuous state spaces, we cannot learn this indicator function because it's 0, essentially everywhere. But the idea is not to rely on sampling this rare event directly. We have seen from before that when you visit a state, you can update like all the rows of the matrix. So we are gonna use the same trick. So we know that the goal G equal S was just achieved for that particular G. So every transition provides some learning signal. So actually we can try to exploit this and expect this gradient of M theta SS to appear in the gradient update. So now this is the main theorem of what is the gradient of G theta, and we will then look at the proof. So consider a model M theta that can be written in this way. So as the little M theta times the dominating measure rho. For this type of loss, the gradient of J can be computed in this way. It's an expectation over two independent samples as S2, sampled from rho, and the next transition starting from S. And we have two terms. The first one, that it's what I was talking about before, because of the singular term. And then we also have the gradient of the next step error. Yeah. So it looks a bit, it's a bit strange because it's not really similar to classical TD learning. We have this additional term here. And what is nice is that during the proof, we will see that we don't, there are some tricks involved in the proofs that are nice to know.
So this,
Yeah.
this m theta is this m theta the f theta we have seen before, like density? Like in the next slide, I guess the m theta is that m theta equals to the f theta. I mean, is the m equals to f?
You mean the norm?
Yeah, exactly. This is just f.
So I define the norm of M to be this expectation of
So small
M divided by rho, essentially.
So small f is small m.
Yes,
Okay.
but yeah, this is more of a definition. But yeah, it's gonna be M theta. So we start with the proof. We have this norm. We can also define the inner product between two measures M1 and M2. So we have that M theta is actually absolutely continued with respect to rho because of the way it's defined, but M theta bar is not because of this identity term. And this identity term will actually make the norm infinite. But the gradient actually is still well defined. And when I say that it's still well defined, I mean that the minima is still the same if after rewriting the J theta in this way, you discard this term here. So you can rewrite J theta from this form in this form. And then you just notice that the minima of the two functions is the same. And the part that actually contributes with identity, it's this part and this part. This part, we can ignore it. It will not affect the minima. This part here, we can work on it. And we'll see now.
What is m theta bar? Sorry, I forgot.
It's the target. So it's the target measure because we are doing a sort of DQN update.
So it's m target and m confused.
So M target is like the target value.
Right.
So it's like the Belmont operator applied on M theta bar.
Oh, I see. Oh, I see. Yeah.
Okay.
Yeah.
So they have the same minima, but they differ by an infinite constant. Funny fact. Okay, so now we are gonna try to compute these two things. So first of all, we look at mtar, which is this identity plus gamma p m theta bar. So mtar, we have this singular term plus the gamma p m theta bar term. This is like an integral operator. So we can just integrate over the next state starting from S. And then we just replace the definition of m theta bar to be little n theta bar times rho. And now we can use this definition and try to compute the inner product. So when we compute the inner product between m theta and m target, the inner product is this quantity here. The definition was in the previous slide, but it's defined this way. This rho can simplify with this rho. And this is just little m theta. So we obtain this quantity here. And then now we replace M target with this quantity here that we computed. So when we multiply M theta S2 with this Dirac mass, this Dirac mass is going to be equal to 1 for S2 equal to S. So we obtain this initial quantity. And the second quantity here, it's by multiplying M theta S2 with this other quantity here. So here the integral becomes over S2 S prime. So the trick is really that under the integral, the Dirac behaves nicely. It's going to be 1. So this is really the inner product. Then we have the first term. The first term is simply it is expected squared value of little m theta. And so when we put everything together, we end up with the result of the theorem. So we have this term because of the singular part plus this term that accounts for the next state transition. And I mean, I think probably looks, I don't know, maybe not super complex, but yeah, let me know. But I think it's nice. I like it that we have this problem of learning indicator functions in continuous domains. How can we do this? And it's still possible to do it in this way.
So I just want to like the minus, there's like
This minus here.
no in the so the gamma above. Oh, I see. So you had minus that thing, minus the dot product thing.
Yeah.
Yeah, because it was the square error.
Yeah. Yeah, and then if you want to write it nicely, you can bring the minus here.
They're really confusing all of that. Okay.
Okay, so this is very nice, but how can we learn a density, this M theta in continuous domains, without like learning a super complex models? Can we use maybe some nice strategy? And the strategy is to use like the some low rank approximation that they called forward-backward representation. And it's essentially the idea is to restrict M to be low rank form. So we approximate this successor measure with a rank R factorization. Although I think later I switch from R to D. And the idea is to write M as the product in each state of two vectors, F and B. F is called the forward vector, forward representation, and B is the backward representation. And you can see F depends on the starting state S, and B depends on the state that you will visit in the future as prime. And what the author says is that F encodes the long-term dynamics starting from S, while B of S primes encodes how reachable state S prime is. So in some latent space, you can think of how well reachable the state S prime is by doing this inner product with F of S. So yeah, the idea is try to find this latent space. It's not easy. But with neural networks, maybe it's possible.
So in the like if you try to apply this, for example, this factorization to tabular things, is that possible?
Yeah.
And what do you get there? Like you didn't like what is the B?
So usually you have low rank matrices whenever the next state transition, it's so in most problems, when you're in a state, you're gonna stay in a neighborhood of that state, right? After one step. So usually those problems have a transition function structure that is identity plus some low rank stuff. And the idea is that M can be written as identity minus gamma P. But if P is identity plus low rank, then the two identities cancel out and you're left only with a low rank matrix. So that's the idea behind that. In most problems, actually, the transition function is identity plus some second order terms. So in problems where in the next state you're gonna be in a neighborhood of the initial state, then this assumption actually holds. And that's also another reason why most papers where they assume the transition function to be low rank actually don't work in practice, because they neglect the identity. Yeah, so that's actually what I just said. Why should it be low rank? Yeah, if you just take a simple linear dynamical system and you see how the state evolves over time. So the state after delta, a unit of time delta, it's always going to be the initial state times I plus some first order, second order terms, and so on. So for delta sufficiently small, it's always going to be similar to identity plus some small stuff. In random diffusions, this matrix here has few small and many large eigenvalues. So when you take the inverse, there are few large eigenvalues. So it's going to be low rank. So results that usually use P to be low rank don't work well in practice because they neglect the identity. There is also a nice connection with SVD. So yeah, this is the approximate version of J. And we know that the minima is the same as the minima of this function. And when you write this using that M is equal to FTB, F transpose B, this is actually equal to this. And this can be seen when you minimize over F and B. This is F and B are actually the SVD of M, the SVD solution of M with rank R. So finding F and B is equivalent to finding the, yeah, this should be R, the rank, R rank best approximation of M divided by rho, because we are looking for a density. And this should be F of S, and this should be B of S prime. It's a type. Yeah, I don't think there is much else regarding the forward-backward representation, but I believe this SVD argument, it's probably one of, like, before I gave you some arguments that maybe were more practical, but I think this argument of the SVD that we're really trying to find the best low rank approximation of M is the most mathematically appealing argument. So when, let's say you have F and B, then it's really easy to compute the value of any function if you're given the reward. And we will see how to do this also in the parallel. The low rank assumption also provides some form of regularization. States that have similar long-term dynamics will learn similar F and B. And this type of low rank modeling also tends to promote learning of the measured dynamical modes of the Markov chain. So you like in dynamical systems, there are low frequency modes, high frequency modes, like I don't know, a steel plate vibrating. You usually try to capture only the main eigenvalues. You don't try to capture everything. So this is kind of similar. This low rank assumption only tries to look at the measured modes of the chain. And this is like a regularization effect. But at the same time, it's also a problem. We cannot really perfectly represent the true M. And so if you want to do some, maybe if you want better results, you need to increase the rank. Yeah, so that's it. Do you have questions? Otherwise, I will go to the last topic, how to apply this in practice. This is still a bit of a mindfuck, so don't relax. Okay. The idea now is to use the forward-backward representation to derive a deparallel method. We start with this low-rank representation of M, and the first idea is to consider a family of policy parameterized by some latent vector Z. And this D should be R, but now let's say it's D. So it's the low rank parameter. So we are looking for a vector that parameterizes the policy, and this vector belongs to the same space of F and B. Now, assume that for any Z, now we parameterize also F by Z.
Right, because the forward backward depends on time.
Yeah.
So, okay.
Yeah.
So only the forward will be.
Also the backward, it could be affected, but what happens in practice is that it doesn't work very well. So the authors just did it on the F. So let's say that for each Z, so for each policy, this actually holds. So that the measure induced by the policy, it's actually equal to this low rank structure. Maybe it's equal plus some small term, some low order term. But let's say this holds approximately with epsilon accuracy. So then pi Z induces this Q value, which can be written also in this way. Then we use that, we can use M, but M can be rewritten this way. So the Q values can be, for any reward, can be represented using the forward and the backward. So now I tell you that, first of all, notice that F now depends also on the action, because we are trying to find a policy. But this F doesn't depend on S prime. So this integral over S prime of B, S prime, RF, S prime, I call it ZR. So actually this ZR is the representation that we are looking for. Because now if I define the policy in this way, this is the optimal policy for reward R. Because when I plug ZR in Q, we get that QZR is equal to this. And then if I take the argmax, then I'm maximizing, right? So the optimal policy can be actually defined this way.
Right, so this is like. Make sure. Oh, so now, so you meant there. So that's Z there, that's the same Z as above, right? So that's just the Q value for like.
So initially I just wrote the Q value for any Z.
Yeah.
And then I say, oh, let's, for a certain reward,
Yeah.
I look at this reward. I look at this ZR. So what is the optimal policy for this ZR? So for this specific ZR, actually, it's simply this argmax, because it's maximizing this quantity here.
Yeah.
So this is actually very, very powerful. If rho is the replay buffer, then you can just take a batch from the replay buffer, compute its average for any reward function that you want. You get your representation, and then you get your policy for the reward.
Should the Z in the argmax be ZR, like the last Z?
Where? Here?
This one.
No, this holds for any Z.
But the other like the F times ZR, right? And
Then I say pi ZR is the optimal policy for reward R.
I think the generalizing for the and
Yeah.
then specifically the R, if we're talking about specific reward.
Yeah. So I define pi Z in this way, and then I plug ZR inside instead of a generic Z. Pi ZR is the optimal policy for reward R.
So I'm confused. So if you like, let's look at the first
Step.
is
Yeah.
the integral, and we put the f z out,
Yeah.
and we're left with ZR, right, inside integral. No.
Yeah. So we are left with yeah.
So, and we want to do the argmax. So it should be fz times ZR, no?
But yeah, I see what you mean.
Yeah.
But if I put ZR here in FZ and also in pi Z, then we obtain this quantity here. And then you just do the argmax.
So I guess it's just notation issue. It's not like, I guess.
Yeah.
Okay, sure. Yeah. That's you're right. Yeah.
Yeah, so ZR is like a representation. So it belongs to the same space as B, and you can think as like we are doing some sort of projection on this basis on the space spanned by B, and because of that we also need this matrix here to be full rank, because in the tabular case we have this result here, so we need B transpose to be invertible. So we, in the loss function that we will introduce later, we also need to account for this. So now we just need to learn the F and B. F is parameterized by Z. We know that M satisfies the Bellman equation here. So the idea is just to do TD learning and use the result from the theorem that I showed you before of the gradient. So we parameterize F and Z by theta. So we define little m theta Z in this way. And then we are just gonna try to optimize this objective here. We're gonna optimize for a random batch of Z and a fixed theta. And the M target is exactly defined like before for a fixed theta bar here. And then we are just gonna use the gradient step from before. Practically speaking, we're gonna use the replay buffer instead of rho. And here little m, it's simply this inner product between F and B. So what happens is that you have two neural networks and you compute this inner product, you compute this stuff, and then you have your gradient. So for example, this is how you could design your network. This is your forward network here. You feed the state and the Z. And then, for example, you could do a double DQN approach where you output two sets of key values and you take the minimal to avoid overestimation. And then you also have the backward network. Here, you don't need to feed any Z or anything, just a state. Here you can see there is a linear layer, layer norm, then this arctangent here. This is a usual approach to extract features. And something also very important is that the output of B should belong to the same space as Z. And here we need to make some choice. The usual choice is to choose the surface of the unit sphere. So the representations and the output of B belongs to the surface of a unit sphere. So this is the final method. During training, we sample a single Z from this surface. We use the formula of byte Z that we saw before, and we collect data using this policy. Then at each time step, we also do the gradient update using this gradient. We update the network, and every n steps, we also do the update of the fixed target network. So it's very similar to DQN. We just need to be a bit careful with the gradient update. We cannot really do the backward of PyTorch, but you need to implement this on your own. But it's not too difficult. We also add this regularization term to ensure the fact that B is full rank. The target,
One question. So FZ is learned, right?
Yeah.
So how are you going to sample from PyZ during training? I guess is your current FZ or what?
Yeah. Yeah, this is gonna be argmax AFZ. Yeah. And the Z is this one that you sample at the beginning, like of the episode. Or every, I don't know, M steps, you resample Z. But you fix that Z at the beginning of the episode, and then you follow trajectory.
But you use like for the pi, I mean, you use the current F that.
Yeah. Yeah, so the problem is of this method is the exploration actually, because it explores according to the current FZ, and it tries to explore in this random way because we sample random Z every time. But yeah, so the exploration here, it's the main weakness, I think.
So how big is D?
Depends.
For the, like for this Mujoko,
Like 32.
oh, it's like small thing.
Yeah.
Okay.
Yeah, it's small.
And the parameterization is what, like you just have this F network.
Yeah.
Takes another, like it's like just like S and A.
Yeah.
And just an extra.
Yeah, you take the state and Z, and then you output the key values over the actions, if it's a finite number of actions. Or you also pass the action at the input if it's a continuous action space.
Yeah.
Right. Yeah, but overall the technique, it's I mean, once you implement it, it's easy, but initially there are some issues. You need this regularization term. The target value, it's a bit numerically unstable. So for example, instead of using the argmax, it's usually a better idea to use the softmax. And also using this combination of linear and layer normalization is usually a good idea. And then at test time, once you have your F and B, we can do what I told you before. For any reward R, you can compute Z in this way. So you sample a batch of data from your dataset, you compute Z, and then you just plug this ZR here and you obtain your policy. So you have like adaptation at test time without doing any computation, really. You don't need to do any additional learning. And this is like a small example. We have 4 rooms. You can see the environment on the right. On the bottom left, you see the starting point. And on the top right, you see a goal state. So here the goal state is actually random. In every episode, it's random. And I simply did the training of FNB as I showed you before. And then I try to do a 2D projection of the representation learned by B. And this is what we see after 10, 25, 50 epochs and 100 epochs of learning. These dots represents the positions in the grid, and the blue corresponds like to one of the rooms, black to another room, yellow to another room, and the red to another room. So we see that indeed the method is actually learning to separate the different rooms in this environment, which is actually pretty nice. So we see that.
This is in their paper.
No, this is I did it. Yeah.
AGI.
AGI,
yeah.
Yeah, I mean it's a simple example, but
What are the rooms? So, the pattern.
so here it's one room. Then there is this small path to go to this room, and then yeah. So these are the walls.
So what's the state in this case
Um,
that you're using?
one-hot encoding of your position in this environment. Yeah.
It's a continuous one.
No,
That
no,
must be tabular.
it's tabular. Yeah, it's tabular. Yeah, it's not continuous because we cannot really. I wanted a simple environment where we can see the representations that we learn. So in this case, I wanted to see if the representation that we learn it's able to distinguish between the different rooms. Yeah, I think it's nice. You can also try to do this with some more complex environment, but yeah, usually you get the best results with this tabular environment. It's a bit difficult to interpret a projection of the representation in a continuous environment if you are like doing some Mushoku stuff. Yeah, so I think this is a really nice approach. It allows you to learn this successor representation, which can be used in many different ways, and can also be used to do this reward-free adaptation at this time.